Hi, everyone. So the office hour this week is moving to? Thursday, same time.
Yeah, go vote.
And it's so that you can all go vote. And so he could go vote. I don't even know exactly for what. I haven't been keeping track, but go vote for something good. And what we're going to do today is continue the discussion about lossy compression, which Pulkit started. Oh, yes.
Can we have like bigger font sizes?
Okay. Thanks for the reminder. Constantly remind until we get to the right size. Lossy compression that Pulkit began to expose. We're going to further develop this notion and the setting around lossy compression and get to also the notion of lossy compression and rate distortion theory and the rate distortion function, which is sort of the analog and the extension of the notion of entropy from lossless compression, which kind of emerged as the answer to what is the fundamental limit on lossless compression. We're going to see that the rate distortion function is what emerges in characterizing the fundamental limits on lossy compression. And for that, we're going to start with reminders of some of the most basic quantities that we've already been exposed to extensively in the context of lossless compression. And first and foremost was the notion of entropy, right? So if we had, say, a random variable or random object x, which was discrete, so x is let's say a discrete random variable, okay, random variable or random object that takes values in some discrete, finite, maybe alphabet, then it made sense to talk about its entropy, right? So then we can talk about the entropy of x, right? And that was, so we denoted it by h of x, and that was defined to be, right, the sum over all the possible values small x that this random object can take, the probability that it takes that value times log, by default base 2, log base 2 of 1 over the probability that it assumes that value summed up over all the values. And we saw how fundamental this quantity is in the context of compression, lossless compression. It answers the question, right, even more specifically, if your data were to come from or be generated by this sort of a source, if it were like a memoryless, right, like if it were IID according to the distribution of this generic x, right, then the best that you can hope to do in compressing data coming from such a source, even if you try to be as as resourceful as you can wish for and work in blocks, large blocks, the best that you can hope to do is, in terms of compression, is these many bits per source symbol, right, per component of your data, which is generated IIDX. And and now of course this carries over, kind of trivially almost to, let's say, if you have a pair, right? So now x and y are, a pair of discrete random variables, right, then we can talk about their joint entropy. So entropy of the pair x, y, and we denote that by h of this pair, right? The h of x, y, and that is really nothing new. It's nothing but this entropy, this time associated with what random object? This time the random object is this pair, right? Just like x was a random object and took values in some, space of possible values. Well, now this pair of variables is also jointly a random object, taking values in some alphabet of pairs. And so it's really exactly this thing. It's the entropy associated with the random object, which is the pair xy. So it's going to be the sum over all the values small x, small y, that this pair of random objects can take, the probability that x is equal to small x and that y is equal to small y, log of 1 over this probability. Okay, so obviously, in terms of operational significance, it carries over from the operational significance of this. If your data happens to comprise IID pairs coming from, the distribution of this pair, then the best that you can do for compressing this data is this, in terms of number of bits per pair. A slightly maybe less trivial extension of the notion of entropy that we've already seen is conditional entropy, right? So let's say the conditional entropy of, let's say of x, of one of these random objects, say x given the other, given y. Right? So that too we defined and we used, and Shubham used it also in the context of modeling sources that go beyond IID. So there, the conditional entropy of x given y is, probably the most natural way of presenting it is as a sum over all the possible values that this y variable can take. So a sum over all the small y's that y can take. And then we're going to take the probability that this random variable or object assumes the value small y. That's going to be the weight that we assign to the conditional entropy of x given that y is equal to small y. Okay? And what is this conditional entropy? That x is equal to, of x given that y is equal to small y? Well, that's really back to this notion of entropy. Okay? This time associated, so, entropy in the end, right, even though we denoted h of a random variable, it's really a function of the distribution of that random variable, right? So here, this entropy is a function, right, of, the probability mass function that describes x, right? Well, here, this creature is exactly this creature, okay? The role of the probability mass function now is played by the conditional probability mass function of x when we know that y takes on this, particular value, small y. Okay, so this thing is precisely this thing, right? So I'm going to sum up over all the values, small x, that x can take. This time, it's going to be the role of the probability mass function on x will be played by the conditional probability mass function on x, given that y is equal to some value, this particular value we're conditioning on. Okay, so again, I'm assuming this is familiar, and in fact, one thing that you've seen, okay, so this we gave it, right? This has the notation h of x given y, right? H of the random variable x given the random variable y. Again, it's a function really of their joint probability mass function. And here it is explicitly. This, again, in the end, this is a number, right? Again, I know sometimes for some of you the notation, and I feel for you, for some of you, this is sometimes confusing because, wait, h of x, it's a function of x, so it's not a random variable, right? It's a number that depends on the distribution of x. And so here too, right, this thing is a number, as are all of these, right, for any small value y. This, these are different numbers. And and one of the things that you'll recall is that, the property of this conditional entropy is that conditioning reduces entropy. So the conditional entropy of x given y is always no more than the entropy of x, right? So recall, and that's also, pretty kind of intuitive, right? If we think of also of entropy as the notion of uncertainty, then you're on average, your uncertainty on x, given that you know something like y, information can only help to reduce the uncertainty. So you're going to always have this relationship, even though, and this is also something that Shubham pointed out, it's possible that for some specific values of y, this thing is suddenly larger than the entropy of x. Suddenly, maybe there's some value of y which is kind of atypical and throws you off, and suddenly you see, wait, y assumed that value? All of a sudden you're totally clueless about what x might be. So maybe, but on average, when you average these over all of the possible, over all the possible values of y, and you give them the appropriate weight, then you're always going to have, on average, reduction of uncertainty with knowledge of something. In this case, knowledge of y can only help reduce your uncertainty about x. And also operationally, in the context of compression, this was also kind of implicit, at least, if not explicit, in some what Shubham talked about in the context of compression, right? This corresponds to, for example, the fundamental limit on how well you can compress, let's say, data coming. Let's say if your data is coming, let's say you have pairs coming IID from according to this pair, xi, yi's, and then you have the sequence of y's as side information for your compression. So both encoder and decoder know the y sequence. Now we want to understand what's the best we can do for compressing x. And the best that we can do is, in terms of bits per source component, is going to be this conditional entropy. Okay, so obviously, side information can only help you to do better. You can always ignore it. So we're always going to have this relationship. Okay, again, I'm assuming that this is kind of familiar, And, but of course, feel free to stop me at any point. And this is enough to present possibly the most important new quantity in today's lecture, which is the mutual information between x and y. Okay, so maybe I'll make sense if I continue here. Can I continue here? Okay, this is going to be right. This is going to be a test to those who are following me, so you know the order. So now we can talk about, in the context of x and y, we can talk about the mutual information. Okay, between x and y. And that we denote, for historical reasons, by I. Well, okay, it doesn't make sense, I information. And we denote it as I, and then we instead of x comma y, for historical reasons that I myself don't fully understand, we're going to write semicolon. So I, x semicolon y is our notation for the mutual information between x and y, which is defined as, or let's say in the context of our current context of discrete random variables, it can be defined as the entropy of one of the variables plus the entropy of the other minus their joint entropy. Okay? So that's what mutual information between x and y is. That's how it's defined. And we can immediately extract or glean some properties of it. So, and in fact, maybe, so let's look at some properties. Now I'm going to totally annoy many of you. Now I'm going to continue here. So I'm going to delete this part. Oh, I could actually continue here. Okay, yeah, this is going to be good. So then it'll be only for...
Only like half of that whiteboard is visible.
Oh, this part?
Yeah, like half of it is visible.
Oh, this part?
Yeah, pretty much.
Okay, well, let's see if I can pull this off, or if I can make use of this real estate. I mean, after all, we're talking about compression. We can't waste space. So let's look at one alternative kind of representation for mutual information. So let me play with this a bit. So I'm looking at the mutual information, and so it's equal to the entropy of one of them plus the entropy of the other, right? Minus the joint entropy. And the joint entropy, as you've seen, right? One of the properties of joint entropy you have seen is that it can be decomposed to the entropy of one of them, right, plus the conditional entropy of the other. Right? So this is one way of decomposing or representing the joint entropy. Everyone okay with this? Great. So now we're getting to, right, so these guys cancel. So I'm getting h of y minus h of y given x. Okay, and similarly, I could have decomposed this as, let's say, h of y plus h of x given y, and then I'd have gotten that this is the h of x minus h of x given y. Okay, so I guess properties. Well, okay, a few things, and this is a bit. Sorry for the mess in the order, but I guess one property which is actually immediate from this presentation is that it's kind of symmetric in x and y. So mutual information between x and y is equal to the mutual information between y and x, right? I guess one way of seeing it is from this presentation, because what are we seeing here? It's the entropy of one guy plus the entropy of the other, right? So that's invariant to the order between them, minus their joint entropy. And it's also pretty, I hope, self-evident that, because entropy really is invariant to, let's say, relabeling or, the order of the elements of the alphabet. So the entropy of x and y is equal to the entropy of y and x. So it's really about, just potentially a different ordering of the values that these pairs could take. Right? So this too is invariant to the order between x and y, and therefore this whole thing is invariant. And then the second thing, which we can easily glean, say, from these representations, taking this into account, that conditioning reduces entropy, is that the mutual information is always non-negative. And a third property, which I'm not going to get into, and maybe it'll be a homework. Otherwise, you're just going to have to wait for next quarter to take 376 and or look at the class notes from 376, is that there's another representation of mutual information, which personally I love most. And that is, so after a few additional steps, you can also get to a representation of mutual information as relative entropy. Remember relative entropy? Everyone remember relative entropy between two probability mass functions? Everyone remember that object? Great. So with a few additional lines of work, you can also show that this is equal to the relative entropy between the, I'll write it like this, the joint the probability mass function that governs the pair xy, and the product probability mass function. So the probability mass function on the pair xy, when they each maintain their marginal distribution, but they're independent. Okay? So that's another alternative representation of mutual information. And some of the reasons I like it is, number one, it gives you another, I think, intuitive sense of what mutual information is. It's a measure of the degree of dependence between the random variables, right? The more dependent they are, the farther away their joint probability mass function is from probability mass function where they're independent. okay? And so the larger the mutual information will be. And the more close they are to independence, in fact, like when they're independent, in fact, only when they're independent, will the mutual information be 0. And this is one of the ways of seeing it, because, only when they're independent will their true joint probability mass function have a relative entropy 0 with respect to the product probability mass function, right? So, and then the other reason why I love most this representation is that it carries over, and on this, again, you're going to have to trust me for now, and maybe even for this whole course, that even though everything we did here was kind of assumed that x and y are discrete, right? So then it made sense to talk about their entropies, their joint entropy, their conditional entropy. But in fact, mutual information carries over and is completely natural. So unlike entropy, which doesn't make sense for continuous random variables, mutual information makes total sense for completely generally distributed random variables. So x, y can take values in wherever you want. They can be discrete, continuous, take values in the real line, take values in abstract functional spaces, the whole sample paths, whatever you want. Mutual information is still well defined through, in fact, a very natural generalization of relative entropy. So you can always talk about the relative entropy between two distributions, not necessarily probability mass functions, but two distributions that can govern arbitrarily abstract random objects. And so you can always talk about a relative entropy between their joint distribution and the product of their marginals. And again, those who want the details will be motivated to come back for more in the next quarter, and also maybe to an extent some of this stuff, how, let's say, mutual information extends to some forms of continuous random variables, as the case might be. If and when we will need it, we will, have you guys work a little to understand how things extend. But for today's discussion, it's fine to just, let's say, initially just focus on discrete random variables, and then at some point just have some faith in me that this thing extends to general, also continuous random variables. So, any questions so far? And so now we're going to start. So how does this have anything to do with lossy compression? Right. So far, just like with entropy. Okay, if you didn't take a course on compression, you'd look at this and you say, okay, maybe there's some reason to believe it's a nice, measure of some uncertainty. But then, you realize that, okay, it actually answers a very fundamental question in lossless compression. So mutual information, too, many people, from all sorts of fields, just enjoy this as a nice kind of measure of dependence between random variables. So they use it for all its nice properties, and there are several other nice properties, just as a statistical measure of dependence that we might expose you to in some of the homework. But much more fundamentally, it arises in answering the most basic fundamental question in lossy compression. Okay, so let's remind ourselves the general setting of lossless compression. Okay. So let's say I have n source symbols that I want to represent. x1, x2, xn. And, right, so I'm going to encode them. So I'm going to design an encoder that represents this n tuple in, hopefully not too many bits. So it's going to output some bit representation of, let's say, m bits. And then the idea will be that a decoder at some point is going to read this succinct representation of m bits, and from that come up with its reconstruction. And when we talked about lossless compression, then here the decoder was required to come up with exactly the original data. So we would here require exactly x1 up to xn. But in the context of lossy compression, we're okay. We might be okay if what the decoder comes up with on the basis of this compressed representation into m bits is something else, hopefully not too far off from this source from the original data. And so we usually also quantify. What does it mean, not too far off? Usually you'll specify to me some distortion criterion. Let's call it D, which for today it's going to be kind of interesting enough to consider, as we often do, kind of so-called component-wise or symbol-by-symbol distortion criteria. So usually you'll specify to me a distortion between pairs, a distortion that looks at the distortion between, the ith component here and the ith component here in the reconstruction. And then I'm going to judge the overall goodness of this reconstruction according to let's say the average, right? The average, or if you will, the per symbol distortion. And of course, this is, as in the lossless case, we're going to be modeling things probabilistically, right? This is going to come from some probabilistic source. So this is a random variable. We're going to look at its expectation. Okay, so this is what we're going to colloquially refer to as the distortion. All right, so this is the distortion that your scheme achieves. If you want to be totally elaborate and explicit, you're going to say, I guess the per symbol, right? Because it's normal, per symbol, because we look at the sum of all these individual distortions and normalize, and then we take expectation. So per symbol, expected distortion, but usually, we just talk about the distortion achieved, and we mean this. And then, of course, the question is, okay, obviously you want the distortion to be as small as possible. And of course, so distortion criteria that you guys may, or some of you are familiar with is, for example, Hamming. So let's say Hamming is a distortion criterion that makes a lot of sense in the context of discrete data. And then we just look at whether or not the reconstructed symbol is equal to the original symbol. So it's an indicator for whether the reconstruction symbol is I mean, if the reconstruction symbol is equal to the original symbol, then there's zero loss. And otherwise we count it as a loss. Right? So that's called examples of distortion criteria. Right? So this maybe this is one, and this is called Hamming distortion. And then, as we said, like lossy compression is also, and in fact, in some ways, even much more interesting in the context of continuous data, where you have no choice but to do lossy compression. And then, of course, let's say if these are real valued, right? These are, I don't know, sensor measurements. These are real valued. Then it makes a lot of sense to look at something like squared error distortion. Okay, so, usually in an application, you'll tell me what is the right, what's the most kind of relevant distortion criterion. Let's say if this is let's say genomic data. These are nucleotides taking values in a space of size 4, and then it might make a lot of sense to talk about Hamming and to tell me, yeah, I'm willing to suffer a bit of Hamming distortion, positive Hamming distortion, meaning in the reconstruction, every once in a while, you're going to get a base pair incorrect if it means that we're going to need way less bits here in the representation than we would if I required totally lossless compression, right? In which case we would need the entropy. So maybe now, if I'm willing to suffer some positive Hamming distortion, maybe we can get away with less bits. And so, okay, so there's a distortion, and then the question of, okay, what does it mean getting away with less bits, right? So concretely, we talk about the rate, just as we did in lossless compression. We had the compression rate, which was the ratio between the number of bits in the compressor representation and the overall length of the sequence, right? So it was like, how many bits do I need per sequence component? So that was the rate. And so here too, that's the rate. It's going to be the ratio between the number of bits, M, that my compressor representation is requiring, and in how many overall source components did I manage to represent with these M bits. So here it's like N source components. Okay, so that's the rate in bits per, usually you're right, bits per source symbol. Or we just say, bits per symbol. Okay, and we know, again, lossless compression, we know that the best that you can do is, in terms of rate, if you want this to actually equal this, or in terms of distortion, if you want, let's say, the Hamming distortion to be 0, if you want this thing to be 0, then we know what is the minimum rate I'm going to need. That's the entropy. Let's say if these are IID according to some distribution X, it's going to be the entropy of X. But the question is now, if I allow some distortion, okay? So maybe we can talk. So here's my question, and I'm not going to be maximally sort of formal about it. And I'm just going to write it in words. So the question is, what is the minimum rate needed, okay, for getting distortion no more than some specified distortion level that you're willing to tolerate. Okay, so again, lossless compression, we've answered this. If this D is 0, what's the min rate that we need for distortion 0? And the chorus sings entropy. Exactly. But what is the minimum rate needed if I'm willing to suffer, let's say we're doing Hamming loss, and this D is, let's say 0.1, right? Meaning Hamming loss, D 0.1, meaning I'm okay with this reconstruction getting only 90% of the symbols correctly. Then we should expect to be able to represent the data with less bits to have a compression rate smaller than the entropy. And this question was answered beautifully, crisply, and quantitatively by Shannon, of course. So Shannon's theorem in this context, or one of Shannon's theorems, so in this context of lossy compression, is that let me also denote. So let's denote the answer by R of D. Okay? So what is the minimum rate needed for achieving distortion no more than D? Okay? When I allow you to optimize over all schemes in the world, arbitrarily complex, sophisticated, using arbitrarily large blocks of data simultaneously, what is the minimum, the best that you can do, optimizing over all of these? Okay, so there's some answer, there's some minimum rate that we're going to need, denoted by this R of D. And Shannon's theorem is that R of D, the minimum rate that you need to achieve distortion no more than D, is given by the minimum mutual information between X and Y. Oh, okay, I should say, so this was very general. I didn't talk about what the distribution of the data might be. So here, again, to be concrete, just like in the context of lossless compression, we talked initially about IID sources of information, so here too. So Shannon's theorem for IID source, so for if the xi's are IID according to some generic x, right? Just like in lossless compression, we know if the xi's are IID according to some generic x, then the minimum rate that you need for lossless compression is the entropy of x. So here, let's again assume the xi's are IID according to x. Then, what's the minimum rate that you need if you're allowing distortion up to D? It's the minimum mutual information between this generic x that represents the distribution of your source components and a generic reconstruction variable y minimized over all joint distributions on xy such that the expected distortion between xy is no more than D. Okay, so just to be slightly more explicit, again, the distribution of the source of these xi's X is given to you. That's not something you can control. That's the characterization, the characteristic of your source of information. Your xi's are IIDX. So this minimization is really over all joint distributions on X and Y, but consistent with the given distribution on X. So this is really a minimization over a conditional distribution on Y given X. Okay, basically over all conditional distributions of Y given X that satisfy this constraint, okay, under which the expected distortion between X and Y is no more than D. Okay, so as it should be, like in the end, this is some functional of just the distribution of X. Right? So we're optimizing over what remains of the joint distribution, which is the conditional of P of Y given X. What else do I want to say about it at this point? Maybe the best thing is to basically go straight to two examples. So two examples corresponding respectively to these two distortion criteria. And so and by the way, everything that I'm doing today will be done in more detail and more rigor, but not pedantically, but still slightly more detail and rigor in 376. And so let's look at one example, or let's say first example is going to be the rate distortion function associated with or for a Bernoulli source. Okay, so in the case of a Bernoulli source, right, I mean, in the end, this is a very wieldy, finite dimensional problem, right? In fact, the distribution on X, if X is, so here I'm going to assume, so more specifically, so X is Bernoulli of some parameter, small p, and let's assume without loss of generality that this p is no more than a half. Otherwise, we can flip it, and things will carry over to the complement. So right, and as we said, and now let's look at the distortion criterion being Hamming. Okay, so in the end, for this problem, solving for this R of D is just a very small, low-dimensional optimization problem because, Y here, the reconstruction variable, is obviously also binary. Right, so again, here, this is the source. These information components are just IID Bernoulli P, just coin flips with some bias P. And so the reconstruction is also going to be, obviously, with, binary. And so this simply boils down to, optimizing for a conditional distribution of one binary variable Y given another binary variable X. So even if you don't, accommodate, all sorts of symmetries that are here, it's a very small number of parameters. Like it's at most, what's it going to be? Like maybe 2 parameters for this optimization problem. But there's also, you can also exploit the fact that there's symmetry. And so, again, if we had more time, and we're going to do this in next quarter, and you can look at the notes, you could easily do the math and get to the fact that for this setting, R of D is simply this. So it's the binary entropy associated with the source. Okay, so the entropy of the source minus the binary entropy evaluated at D, the distortion level, at the interesting region where the distortion is between 0 and P, and 0 for distortion more than P. Guys, can you remind me, or have we already introduced this notation or the binary entropy?
We used it one time, but
Maybe.
Okay, so just in case, right, when I write binary H2 of, say, Q, okay, I just mean the entropy of, I don't know, let's call it Z. Okay, for Z, Bernoulli variable of parameter Q. Okay, so this is what we, so for this, we're calling it the binary entropy function, and I think you've even seen what it looks like. And so, in fact, if you need a quick reminder, the binary entropy function, right, what does it look like? H2 of, let's say, Q. It's kind of symmetric around a half, and it does something like this, right? And here, and this corresponds to the maximal value corresponding to the entropy of a Bernoulli half variable, a fair coin flip, which is 1. Right. So that's a binary entropy function, and so the rate distortion function here. Let's see what the rate distortion function here boils down to. Let's see if it makes sense. It starts so here now I'm plotting R of D. R of D, the function of D. Let's see. So at D equals 0, I have H2 of 0 is 0. So I have, so I start right here at binary entropy of P, which is the entropy of my source. So that's where I start. And then I get all the way to distortion P, where at distortion P, I have this minus H2 of also P. So that's 0. Right, so I'm taking this constant value and subtracting from it like this thing, right, until I get to value P. At P, I'm going to get to 0. And then starting from that point, it's going to be 0. Right, so let's see. This kind of, that it makes sense. At least some sanity checks. So at distortion 0, lossless compression, what's the minimum rate I'm going to need? The minimum number of bits per source symbol I'm going to need? Well, we know it's the source entropy, right? And the source entropy is indeed the binary entropy of P, the Bernoulli parameter of the source. So that corresponds to distortion 0. Obviously, starting from distortion P and on, I don't need to tell you anything about the source. I don't need any bits of representation here because I'm just going to reconstruct with let's say all zeros. My reconstruction is going to be all zeros, and so on average, my expected Hamming loss is going to be P, right? Because, again, my source is going to be 1 only with probability P. So with probability 1 minus P, I'm going to get it right on each of these components. So my expected distortion is going to be P if I just have reconstructions all zeros, and for that I don't need you to tell me anything about the source. So that's this part. Another thing that we're seeing here, which is in fact not coincidental, and is true of all rate distortion functions for any source, is this convexity. And maybe one, not to belabor this point too much for lack of time, but let's for example look at this midpoint here. Let's see, corresponding to distortion P over 2. And so let's look at, let's say, this the half of the entropy of the source entropy. Let's look at this. So basically, this point right here. Okay, this point corresponds to P over 2 and binary entropy of P over 2. Why would or should this point be above the value of the rate distortion function? Because this point corresponds to something very trivial that you can do, right? You can just decide that, okay, half of the data, like the first half, I'm going to describe losslessly, and so I'm going to need entropy bits per source symbol, but it's only going to be half of the data. So when amortized over the full data, I'm only going to use these many bits per source symbol, and then the other half I'm not going to tell you anything about and just guess or reconstruct it with all zeros. So on the other half, you're going to get, as we discussed, average distortion P, but it's only going to be on a half of the data. So overall, amortized on the full data, you're going to have this much distortion. Okay, so this point right here corresponds to a stupid kind of time-sharing scheme, if you will, that time shares between these two extreme points. Okay, but obviously there are smarter things that can be done, and those smarter things will get you all the way here. And what are these smarter things? I hope to give you a bit of an intuition with the next example. I should be striving for allowing you about 10 minutes at the end, which means I have order of 11 more minutes.
You can even play.
Okay, thank you. Very generous. Okay, so is everybody more or less good with kind of the main, kind of the essence of this story? I know that there are, I didn't go into all the details, but feel free to ask me anything about this. Okay, so while you think about what you may want to ask, let's continue here. Let's look at example 2. So example 2 corresponds to a Gaussian source. So here, X, let's say, is standard Gaussian. Okay, so now your source components, X1, X2, are IID standard Gaussian. And the distortion criterion we're using is squared error. Okay, so your source components are now real valued. Also, the reconstruction components here are naturally going to be real valued. So it makes a lot of sense to, for example, look at the squared error. And for this problem, the miracle so happens, and again, maybe some of it will give you a taste for, otherwise, as usual, wait for next quarter. The miracle so happens that even though this is ostensibly now an infinite dimensional optimization problem, because now we need to optimize over, conditional PDFs of y, which is a real value random variable given x. So that's an infinitely dimensional object, but you can actually solve this thing very explicitly, and it's in fact not hard to do, due to some properties of the Gaussian distribution and how well it gels with squared error distortion, and some maximum entropy properties that we will get into in the next quarter. And so you bring these properties together and you solve this, and you get that it's equal to 1/2 log of 1 over d. Okay, where it matters for the interesting range of d no more than 1 and then 0. Okay, so let's see that this makes sense, let's look at let's see what it looks like. Okay, let me plot it here. It looks something like here's R of D, here's D, and here's 1, and starting from 1, it's 0, and then for D less than 1, it's doing something like this. And so let's see that it makes sense. For D more than 1, again, the same kind of argument. If the variance of your source is 1, right, then to get distortion, squared error distortion per symbol no more than 1, I don't need to know anything. Don't give me any information, any bits. Again, my reconstruction is going to be all zeros. And then the expected distortion between the actual realized value and my reconstruction is going to be the variance of the source, 1. So I don't need any bits of information about the actual realization of your source to get distortion, 1. And then, but if you want something non-trivial, you want smaller and smaller distortion, we need more and more bits per source symbol. And as Pulkit discussed in the previous lecture, obviously here we're talking about x, which is a continuous random variable. So and so first, in the sense, we can't talk about its entropy. Its entropy is obviously infinite. So that's one way of understanding, why this would, for a discrete source at distortion 0, this would be the entropy. But now it's a continuous source, it has an infinite entropy, and obviously, right, if we, as sophisticated as we try to be, if we want to get more and more fine with describing the source components, we're going to need to put in more and more bits of representation per source symbol. Because again, it's a real value. You're going to need infinitely many bits of precision if you really want to actually nail it. Okay, and by the way, you can also, maybe I'll mention it, that as you can imagine, just like we can talk about rate distortion, which is the minimum rate you need if you require a certain level of distortion, you can also flip this, and similarly, you can talk about the distortion rate function, like what's the minimum distortion that I can achieve if I'm allowed to dedicate no more than r bits per source symbol. And so you can easily flip this function, and you're going to see, and you're going to do the exercise, and you're going to see that it's this much. Okay, so this is the squared error, the mean square error per symbol that you can get, the absolute minimum that you can get if you were to optimize over all schemes in the world, arbitrarily sophisticated. It's basically flipping this thing. So d of r here. So d of r for this source would start at 1, right? Obviously with rate 0 bits per source symbol, okay, I'm going to get mean square error of 1, the source variance, but then the more bits I'm willing to expend per source symbol, the smaller my distortion, and so this thing is 2 to the minus 2r, which I don't know if now is the time to get into it, but and maybe we'll have a homework exercise, but Pulkit, did you last time actually compute, let's say, how much distortion you're getting with it? Let's say you're looking at 1 bit per Gaussian component, but with scalar quantization. What was the distortion that you got? Did you actually do the computation?
We didn't compute the distortion, but we computed the code words.
Okay. So you could do the math, and so let's say at rate equal 1, right? At rate equal 1, meaning I'm willing to dedicate 1 bit of representation per source symbol. Then you could do something simple, like Pulkit, you guys went over with Pulkit, such as just for every source symbol separately, just give me 1 bit to tell me if it's positive or negative. Okay, so it's going to be 1 bit per source symbol, so that's going to correspond to rate 1, and you can do the math for that scheme. What was the distortion that it got? And it got something. Okay, it got something. But now you can compare it to this, which is the optimum. This is the optimum that you can get with 1 bit per source symbol, but you're going to have to work hard. You're going to have to work on a large block of data, not something as simple as symbol by symbol, just 1 bit of quantization for every component separately. And to get a sense for maybe how hard you might try to work and how much better this might be, let's actually try to get some intuition regarding the form of this thing. So if you look at like typically, right? So with high probability. So remember we had this, all these discussions about typicality for discrete data. Well, you can also talk about typicality of continuous data. And here, rather than talk about like sizes of sets in terms of number of elements, you can talk about volumes of sets. So here with high probability, if I look at a realized n-tuple from this source, IID normal, 0, 1, right? Then I can look at, let's say, the sum of the square of the realized components. And, right, so these guys, the square of these xi is, what is its expectation? What is the expectation of x squared? Right, so x is normal 0 mean, variance 1. What's the expectation of x squared, second moment of x? 1, right. So here I'm looking at an average of these guys, which are IID with expectation 1, right? So again, the law of large numbers tells me that this average is going to be around, with high probability, this average is going to be close to the expected value of each of these, which is 1, right? Certainly no more than that. Right? So this is, again, just kind of a law of large numbers type argument. And if you'll allow me to put the n here, and again, to make this rigorous, I'd need an epsilon and all sorts of things, but I give you guys credit that you don't need all the epsilons to get the main point. Right? So with high probability, we're going to see a realized n-tuple, which satisfies more or less this, or, if you will, let's look at the square root of this thing. Okay? So if I think about the, if I think about the realized n-tuple as a point in n-dimensional space, right? So let's say that this board here now is all of Rn. Okay, then what I know is that with all likelihood, the realized source n-tuple is going to fall inside of an n-dimensional ball of radius essentially no more than square root of n. Okay, and now let's see, what can one possible reconstruction take care of? Like so in a sense, I know that I need to worry about covering, if I want to achieve distortion D, I need to worry about covering like the sequences in this typical ball, if you will. I need to cover all of them within distortion, essentially no more than D. Now, any particular possible reconstruction, code word, if you will. By the way, maybe this is also a point to point out that talking about representation of size m bits is actually equivalent to having a code book, a set of possible reconstructions of size, let's call it capital M, which is 2 to the power m. So this is going to be size of codebook, which is in turn the set of possible reconstructions. Right? Because you can think of any one of these sequences of bits as, if the decoder is going to see a certain sequence of bits, it's going to come up with one possible reconstruction. Right? So if it has, you have 2 to the m possible reconstructions that this decoder might come up with. Okay? So instead of talking about like the number of bits, I can talk about just the number of code words, of possible reconstructions that this decoder has. And so let's see what one particular reconstruction, what portion of the possible source sequences is it going to be able to cover to within distortion D. So basically, I'm asking, for a particular possible reconstruction, I'm asking, so distortion D, again, per symbol, distortion D would correspond to, right, so it would correspond to, if we don't normalize, it would correspond to the set of, basically, a ball of radius no more than square root of nd. Okay, so for a particular possible reconstruction, this is the set, the set of sequences that are covered by this reconstruction to within distortion no more than d is this ball of radius square root of nd around the reconstruction point. Okay, so why square root? Because because if we don't take the square root, then it's just the sum of the squares, and that's how we define the squared error, the sum of the squared. But with the square root, it gives us the actual length of the vector, and then also we have the n, because when we talk about distortion D, we normalize, right? Distortion D corresponds to the sum of the square of the components divided by n being no more than d. So the overall sum is no more than nd. So the overall square root of the sum is no more than square root of nd. And so then the question is, okay, well, if I want to get for distortion no more than d, right? How many of these code words am I going to need in order to cover this typical set? Well, at least, so size of the code book, right, this capital M, is going to have to be at least, right, from a volume preservation argument, it's going to have to be at least the ratio between the volume of the big ball to the volume of these kind of smaller balls of radius d. Okay, so the big ball is the ball, the typical set. It has a radius. It has a radius of square root n, right? So it's it's some n-dependent constant, but it's proportional to the radius of the ball, which is square root n to the power of the dimension n, right? And then the size of this small ball is again the same n-dependent constant. This time, the radius is nd to the power n. Okay, so that is so that's 1 over d to the power n over 2. Sorry, I'm out of time. But hopefully you guys can be with me just to finish this. Right, so, okay. So basically that's that's the size of the code book. And I get this, okay. And so the rate that we're going to need, right, equivalently, the rate, which is, what was the rate? I erased it. The number of bits divided by the number of source symbols, which in terms of the size of the code book, right, it's log the size of the code book divided by n. That's going to have to be at least, so size of the code book is at least this, so log of that is at least n over 2 log 1 over d, and then divided by n. Okay, so that's the 1/2 log of 1 over d that I just erased. The rate distortion function, right? This thing is 1/2 log of 1 over d. So this kind of volume preservation argument tells you why you need at least this much. You need, the rate has to be, at least 1/2 log of 1 over d. And now when you look at this in 2 dimensions, right, you'd say, okay, but if I want to actually cover this thing with these smaller balls, I'm going to need a substantial amount of overlap, right? But what happens in large dimensions, when n is large, in fact, you can be, this sort of covering is very efficient. And the overlap here, so in 2 dimensions, it's not true, but when n is large, the amount of overlap becomes very insignificant. And so basically, you can actually achieve this. You can actually, you don't need more than essentially this ratio of number of these small balls, so size of the code book. And in fact, then you can ask, okay, well, how do I actually choose these code words, these ball centers? How do I choose them? You don't even have to be too careful, too judicious. You can actually randomly select these points. You can you can characterize the distribution from which you merely need to sample randomly to get these reconstruction points. And that's in fact the way that we prove that this minimum mutual information is achievable. It's true, like specifically for this example in the Gaussian case, but in fact, quite generally, this sort of a picture carries over for general sources, general distributions, distortion criteria, and so on. I know this was a lot to take in, and I also apologize for taking more of your time than I deserved. So I guess now you have no time. You have minus 4 minutes to...
So, I'll upload this set of slides which have last year's quest solution, and we looked at the plot in the last class, right, where we looked at how the RD, like the point which Tsachy was making, that in practice we can get some rate distortion performance, and how does that compare to the optimal performance, which is given by half log, actually sigma square by d or 1 by d. And so that plot is also in the Equalab notebook from last lecture, and we'll also upload just these slides. So you can compare like that exact point with Tsachy made there. Just how much extra work do you have to do compared to like some simple scheme to get to the theoretical optimum.
Okay.
Yeah, I'll also
Right, well, I'll try to reinforce the important stuff beginning of the next lecture. So thanks, guys, and happy to take more questions offline.